We have discussed ultrafast processes in molecules at length, not really at length, because it is really a vast field. We have talked about only some of the processes. We have not talked about even things like fret that we promised to discuss, and we have not talked about photoisomerization. Ultrafast dynamics in molecules is really a very rich field, which has been pursued for a long time, and there are like thousands of good papers that one needs to read. But then in this course, we cannot really go through the entire body of literature that is there in this field. We can only introduce you, and then it is up to you to read and learn more. So, and we have to finish in a given time frame as well. So, what we will do now is that we will keep molecules aside, and we will move on to things that are of great interest over the last 20-25 years. So, we will talk about nanoparticles. Today, we are going to talk about plasmonic nanoparticles to start with. Then we will talk about what happens when you break down nanoparticles further. Is there something between molecules and nanoparticles? That is called nanoclusters. And today, we are focusing on things like gold. When you talk about nanoparticles, generally you would be interested either in gold, silver, all these things, metal nanoparticles, or you would be interested in semiconductor nanoparticles. We have done a lot of work on silica as well, but for now we will not get into that. So, after this we are going to talk about semiconductor nanocrystals, solar cells and perovskites. So, for now let us begin our discussion on plasmonic nanoparticles. What is the meaning of a plasmon? What is a plasmon? Can somebody tell me? Yeah, that is phonon. Quantum of vibration is phonon. See, electron is like unit charge, right? Quantum of charge. Phonon is quantum of vibration. Photon is quantum of light. Similarly, plasmon is also quantum of something. What is that something? The name suggests that it is plasma. Plasma we have studied from childhood that it is the fourth state of matter. Plasma essentially means ionized gas. Now, here we are not going to work with gases. We are going to work with what happens when you ionize the gases, you set electrons free. So, plasmon is essentially a quantum of free electron that is present mostly on the surface of metals. So, this surface plasmons have been of lot of interest over the last 25 years or so. This phenomenon called localized surface plasmon resonance is quite well known, more or less well understood, and it has been used extensively to do things like augmentation of signals, enhancement of fluorescence. So, you might well, I do not think I mentioned this earlier. We have talked about radiative rates and non-radiative rates. Now, generally in whatever molecules we have discussed so far, we have only talked about suppression of non-radiative processes, so that the fluorescence quantum will goes up. But there is another way of doing it. The other way of doing it is to play around with the radiative rate. Of course, you understand radiative rate constant is directly related to Einstein's B coefficient, which is related to epsilon. So, you are basically saying how one can increase epsilon, and one way of doing it is by using plasmonics. Joseph Lacovich especially has done a lot of work on this. He started with silver islands and then he worked with silver nanoparticles as well. So, using it, what you do is you enhance Kr. What happens when you enhance Kr? Radiative rate constant, fluorescence quantum will goes up, right, but lifetime goes down, because do not forget lifetime is 1 by Kr plus Knr. So, Kr appears in the denominator of lifetime. So, lifetime going down with fluorescence quantum will going up, provided no mistake has been made, is a sure shot signature of what Lacovich likes to call radiative rate engineering, and that is done by using plasmonics. In fact, nowadays SPR spectrometers are available commercially, where one can enhance the signal from weakly emittive samples and all, and it is used extensively in things like sensing. So, that is why surface plasmon resonance is interesting and useful. So, now where does it come from? We will paint a very qualitative picture. Actually, there is a lot of theory that one needs to discuss if one needs to understand surface plasmon resonance quantitatively. We will not try to do that in the limited scope of this course. We will just point you to this picture that is available, I think, even in Wikipedia. So, what happens is in metals, why are metals conducting? The simplest theory that is used to describe conduction of metals is that of free electron theory, right. So, where one says that since the work function is small, all the electrons are more or less free, they can move easily and so on and so forth. So, what happens is these electrons form sort of a cloud, the free electron, and then you have a hard core, that is the metal nanoparticle, noble metal nanoparticle. We are going to talk about gold almost exclusively, we will refer to silver and platinum and nickel once, but in this discussion as well as in the nanocluster discussion, we will talk mostly about gold. That does not mean gold is the only thing, other metal nanoparticles also give very good surface plasmon resonance. So, what happens is this is the gold nanoparticle, let us say, and this is the cloud of electrons you can think. So, this cloud of electrons can oscillate, and what happens when they oscillate? If the cloud of electrons goes up, then in this ensemble the top portion is slightly negative, partially negative, and the bottom portion is slightly positive. So, you create a dipole. When it goes down, then the bottom portion is slightly negative, the top portion is slightly positive. Okay. So, what you have essentially is you have an oscillating dipole due to the movement you can think of this surface plasmon. That is almost always depicted in this manner. You see the surface plasmon going down, then this side is minus, and here the metal ions you can say are exposed a little bit. So, this side is plus and here it is the opposite phase. So, now what you have essentially then is that when the surface plasmon going up and down, you create an oscillating dipole moment. Once again, let me reiterate that we are painting a very qualitative picture here. So, what happens when you have an oscillating dipole? If you remember what we studied in basic molecular spectroscopy courses, why is it that polar molecules are microwave active? Because when the dipole moment rotates, the z component of dipole moment fluctuates, it goes up, comes down to 0, goes to the opposite direction and keeps on oscillating. Here also this oscillating electric field is set up, and you can think that that electric field can interact with light that is incident on it. Okay. And that is why there is an absorption. Remember, in the classical picture, absorption of light is always associated with resonance between the electric field of light and some kind of fluctuating electric field in the molecule or material, whatever it is. So, when the frequencies match of the oscillations, that is when resonance is achieved and light absorption takes place. All right. Now, this frequency of oscillation depends on several things. First of all, composition. You might think, what am I talking about? I mean, just said gold nanoparticle. So, where is composition coming from? We will come to that in a few minutes. Geometrical shape. If it is a sphere or if it is a rod or if it is a prism, we have different kinds of oscillation. In fact, when it is a gold nanoprism, you can have many kinds of oscillation. So, you have a really broad surface plasmon resonance. And nature of the chemical environment. What do you have around it? Do you have a coat of silica? Do you have polymer? Do you have solvent? Even that is important, and we will see why that is important. Before that, let me show you at least one spectrum of, you can see this is one of the earlier works, 2000, 19 years ago. This is the kind of spectrum that you expect to see in, well, what we conventionally call absorption spectrum. Okay. So, what you can see is at 2.5 nanometer, you can see a band forming here, 4.6, 15, 60 nanometer. Now, here the band has become prominent and it is quite sharp, right. Then when you make bigger nanoparticles, when you go to 120 nanometer, there is a further redshift and then it becomes really broad for different reasons. We will not go into that. That is not really what we want to discuss today. What we do want to discuss is what happens after you excite this. So, essentially when you excite the molecules, there is excess energy, not molecule, sorry, a nanoparticle, there is excess energy in the nanoparticle and it has to equilibrate. It equilibrates by several mechanisms. First thing that happens, the fastest one is electron-electron scattering, right. So, you have this electron here, a lot of electrons around, remember it is a plasmon, right, lots of free electrons are there. So, electron-electron scattering gives rise to reinstatement of the ground state, if you want to call it that. Okay. The other thing that can happen is that you can have electron phonon coupling. Phonon is basically this lattice vibration, right. When we talk about a solid, now you cannot talk about normal modes of molecules anymore. You must talk about the vibrations of the lattice as a whole. As we have seen earlier in this course, many new kinds of vibrations can arise when you have association, like what happened in water. Remember what happened in liquid water? We did not have just the symmetric stretch and bend and asymmetric stretch. We also had librational motion, and that too were of different kinds. So, similarly here in lattice, which is an even more associated system, you have different kinds of vibration, and these vibrations can be activated further if the excess energy is transferred to them. That is called electron phonon coupling. And then what happens is, if you remember what happened in water, you excite one mode of vibration and then the energy gets transferred to things like libration, right. The same thing happens in the crystal lattice as well. One kind of phonon transfers energy to another. So, that is called phonon-phonon coupling, and that is how the heat gets dissipated. Heat means excess energy here gets dissipated. Okay. I should mention here that for the initial slides, I am grateful to my student Bala. He is the one who made it, and he is the one who sort of taught us in our group about the surface plasmon resonance and stuff. All right. So, now this electron scattering is the fastest, and we will show you some data later. That takes place in hundreds of femtosecond, really fast. Then you have electron phonon coupling that takes place typically in 1 to 4 picosecond, and phonon-phonon coupling is the slowest step that takes place in 100 picosecond. So, let me show you another diagram other than this, where the relaxation is divided into two kinds, radiative and non-radiative. The non-radiative processes are essentially Landau damping involving electron hole pairs and elastic scattering, which causes dephasing, and radiative decay consists of scattering of photons, and there is some what you can call fluorescence as well. We are not going to discuss the topic of photoluminescence of gold nanoparticles, but I will give you a recent reference at the end. This is an interesting thing that has come up over the last 5 years or so. It makes sense to read it by ourselves. What we will do is, we will mostly present to you literature from this review that was published 8 years ago. It is by Heartland. So, what this review does is that it discusses in a good amount of detail the dynamics post excitation of noble metal nanostructures. This is one review that I recommend that everybody should read. We are not going to discuss everything in the module today. There will be a lot of things that are left for ourselves to read. All right. So, let me start with by showing you a piece of transient absorption data recorded by El Sayed's group. Link at that time was a student or postdoc with El Sayed. So, what you see is this one on the top for your reference is the extinction spectrum that I showed you a little earlier. This is your surface plasmon resonance band, and the main feature, the dominating feature in the transient absorption spectrum is a ground state bleach that exactly corroborates with this band. And what Link and Elsesser and other people did was that they looked at the ground state bleach recovery dynamics, and they got two time constants. You can see the trace here, two time constants 3.1 picosecond and 90 picosecond. 3.1 picosecond was assigned to electron phonon coupling, and the longer 90 picosecond component was assigned to phonon-phonon coupling. So, what did they not see? What is it that they missed? They missed something, right? There are three processes. So, electron scattering is missed because it is too fast for the resolution of the setup they used. We are going to show you some data there as well. Now, there is a very important difference between molecules and materials. When you talk about materials and you want to do pump probe spectroscopy with them, some interesting feature arises. Well, you have seen earlier in case of 7-aza indole also that if you pump at higher energies, lower frequencies, What happened there? There was an additional fast component due to S2 to S1 relaxation, right, or due to relaxation of S2 just you can say. So, something similar, but more prominent happens in nanoparticles, because you see the absorption is really a continuum, except for that well, it is not a continuum, but there is a peak and then it just goes up. So, you in principle you can excite in you can pump in many different wavelengths, but if you pump at higher energies, not only for plasmonic nanoparticles, but also for semiconductor nanoparticles, interesting phenomena start showing up, especially for semiconductor nanoparticles. So, that is what we will discuss in one of the future modules. So, here what is important is when you want to talk about some time constant, you should not forget what the pump power is. One thing is you can excite at higher energy, the other thing is if you excite by a greater pump power, then a lot of interactions can happen. And this is an example of Heartland group as early as 2000. What they showed was that you look at these decays at different pump power, the tau, the electron phonon coupling time constant actually goes up, right. That is due to further interactions that are there. Now, what they showed is that first of all, if you look at this time constant, how do you know what the time constant is? So, what they did is in this graph in the inset, they extrapolated it to 0 pump power. So, this is sort of like the infinite dilution we must have read, right. Actually, you cannot achieve infinite dilution, but you always extrapolate and find out what it is. So, by extrapolation they found that at notionally 0 pump power, the electron phonon coupling time constant is equal to 0.65 picosecond, which interestingly is exactly the same as what is there for bulk gold. Okay. With increase in pump power, the time constant becomes longer. The time constant becomes longer means what? Coupling is more efficient or less efficient? Yeah, less efficient. Why? Because radiative, not radiative, the rate constant is actually reciprocal of tau, right. So, when you talk about coupling, you have to talk about the rate constant. And then the interesting thing that they showed here is that this time constant they got when they plotted against diameter, and again this is a semi-log plot where the x axis is logarithmic, so that they can show data from say 3 nanometer all the way to 120 nanometer. The time constant remains exactly the same irrespective of the size of the nanoparticle. Okay. This is one thing. Now, let us see an example where the electron-electron coupling is actually observed experimentally. This time it is not gold, it is silver. This is the work of Breuer and co-workers once again way back in 2000. Here you see what they have done is they have done an experiment at a very good resolution. Full scale here is 1 and you can more or less understand how many points there are. It looks like a straight line, isn't it? A little uneven straight line. So, wherever there is change in slope, that is a point. So, there are maybe 500 points or more within this 0 to 1 picosecond time window. And also note the quality. This quality is excellent, right. It is a linear scale, y axis is linear. There you get this kind of data. I mean, if I don't tell you that x axis is in picosecond and I tell you it is TCSPC data, you might believe. This is excellent data. So, that is why they could get this small time constant. Data quality has to be outstanding if one wants to talk about very precise measurements. So, this electron-electron coupling time was found to be, where is the electron-electron coupling time here? You are excited and then see there is a rise, right. Why is there a rise? Because equilibration has to take place among the electrons that are there. First you have done a quantum of excitation that has to get redistributed among all the electrons before anything else can happen. So, that comes up actually as a rise, and this rise time is found to increase from say 100 femtosecond to 300 femtosecond, the second plot, depending on what the nanoparticle radius is. Right now, do not worry about what this line is or what this curve is, just look at the points. Remember, this is silver and it increases from, actually their observation was with 2 nanometer. So, there about 150 femtosecond time constant was there and it went up to 300 femtosecond. And from the data you can see that the trend is there, it is not a fluctuation. Once again, it is impossible to get believable data. I mean, it is impossible to differentiate between 300 femtosecond and 150 femtosecond if you do not have data of this kind. I am sure this was a very, very painstaking experiment, especially 19 years ago. Okay. So, we have talked about spherical nanoparticles so far, gold and silver, and we have shown you what the electron scattering time is in the last slide, and we have talked about electron phonon coupling as well. Phonon coupling is just the longest time scale that you have here. So, this is where we will end this module. In the next module, we will talk about gold nanorods and composite nanoparticles.